All right, welcome. Today we are talking about probability with permutations and combinations, which is basically going to be following up with what we did last time, where we were talking about how when you have multiple events, the way to kind of figure out the probability is to do all of your events separately and multiply everything together. So the first thing that we need to talk about to be able to understand how this is going to work today is the idea of a factorial. A factorial is basically a shortcut for multiplying a bunch of numbers that are counting down. So if you want to denote a factorial, you use an exclamation point. So if I wanted to figure out, say, 4 factorial, it's basically telling me to multiply the numbers from 4 all the way down to 1. And I can find this on my calculator by hitting math and going over to where it says probability, and it should be about the 4th one down. Alright, so how are we going to use this in an actual probability? Well, basically we're just going to use this as a shortcut for figuring out the number of ways that certain things can happen. So if we look at our example, we've got Shanice and Renee, who are members of a lacrosse team. There's 20 girls are on the team, and each person is assigned a number from 1 to 20. We want to know the probability that Shanice gets 1 and Renee gets 2. So, like we were saying before, with probability, you need a number of ways that something can happen out of the total number of possible outcomes. Well, if I've got 20 jerseys and I'm handing them out to 20 people, I know that the numbers can't repeat, right? Nope. Once number 1 goes out, no one else is getting that number. So if I was doing this like last time, I would multiply 20 and then 19 and then 18 and then 17, so on and so forth, because every time I hand out a jersey, there's 1 less to give out. So the total number of ways I can hand out the jerseys is 20 factorial. For the number of ways in which Shanice and Renee can get those 2 specific numbers, well, if they've already received their jerseys, that means the other 18 players can have their jerseys handed out in any way. So 18 factorial out of 20 factorial will give me my answer. And if I type that on my calculator, I get 1 out of 380. A permutation basically means like a number of ways that you can arrange something. So if you are trying to calculate permutations, it's basically like you're doing a factorial, but instead of going all the way down to 1, you're only counting a certain set of numbers. So, if we look at example 2, we've got 15 students. We're going to take these 15 students and assign 3 jobs, right? 3 positions to these students. One of them is going to be named president, and then we're going to choose a vice president and the secretary. And we want to know the probability that Sam, Valencia, and Deshane are chosen for those 3 jobs. So I've got 3 jobs to fill. I need a president, a vice president, and a secretary. And I know that Sam needs to get the first job, Valencia needs the second, and Deshane gets the third. Since that is so specific, there's basically only one way that we can do it to where those 3 people get those 3 jobs, because if I change the jobs at all, I've messed up my permutation. So if we were doing this last time, to figure out the total number of people, there would be 15 people available for president, but then only 14 for vice president and 13 for secretary, because we're not giving the same job out twice. So instead of writing 15 times 14 times 13, I can shortcut it and say 15p3, because there's 15 people, and I only want to do the factorial for the first 3. You can find this on your calculator in the same spot as you did the factorial. You'll notice it's just a couple spaces above it. So if I type 15p3, I get 2,730. So the probability of getting that exact answer or that exact arrangement is 1 out of 2,730. All right, so for example 3, we're going to look at what happens when, this is what's called distinguishable permutations, meaning that even though I have a certain number of things, if, say, the letters in the word are identical, you can't really tell which S was which when you rearrange the numbers. When you rearrange the letters. So if we are given a series of letters, we want to know the probability that we randomly arrange them and get the word Mississippi. So if I look at that and count it out, there's 11 letters that I've been given in the word Mississippi. So I know if I want to rearrange those in a random order, I could do it by calculating 11 factorial, and that would tell me the total number of ways. However, when I look closer, I realize that a bunch of the letters repeat. Right? So these 4 I's cannot be distinguished. I can't tell them apart. So when I start jumbling up the letters, I don't know which I is which. So to sort of decrease the total in such a way that it eliminates the extra counts, I'm going to divide by 4 factorial because that was the number of ways that the I's got switched up. Similarly, I can do the same thing with the S's. And I can do the same thing with the P's. So the extra factorials on the bottom are reducing the total in such a way that I'm removing the extra counts, if that makes sense. So if I type that on my calculator just the way you see it, we get 34,650. Of course, we know that the word Mississippi can only be spelled in one way. So the probability of me randomly rearranging the letters and actually getting the word is 1 out of 34,650. Example 4 is what is called a permutation, circular permutation. Basically, instead of lining things up in a row, we're going to put them around in a circle. This is important because if I don't specify where I'm actually counting the numbers from, we don't know whether we're starting from the top or the bottom or one of the sides, then it kind of works the same way that the indistinguishable permutations worked. So, for example, if I look at this bracelet, there are 6 charms. If I ask you how many different ways I can arrange the 6 charms, then it's technically 6 factorial, right? There's 6 things and I can put them in any order that I want. Unfortunately, I didn't tell you where to start counting. So the first charm could have been in any one of the 6 spots, and the arrangement would still stay the same because I'm sort of rotating it around. So if I do that, I would have to divide the 6 because, again, I didn't know which of the 6 spots to start counting from. If I do that, I would get basically the same thing as if I had started with only 5 objects. So if you look at the formula box above this, it tells you that if you're doing a circular permutation without specifying where to start, instead of the number of terms in a factorial, it's the number of terms minus 1. So of course, if I want the probability that I rearrange the charms in a random order and get the specific charm that's in the picture, well, there's only one way to get that exact charm, but there were 120 different ways I could rearrange the charms, so it's 1 out of 120. For part B, they did give you a reference point, right? So you've got a table with 4 people, and you want to know the probability that the person who paid for dinner is next to the window. So if I have my table, and let's assume I have the window here, the person who paid is sitting here. I know that that's where I'm sort of rearranging everything from. So I know that if the person paying is sitting next to the window, the other 3 people can be arranged in whichever order I want. And if I'm figuring out the total number of arrangements, then I would have to count all 4 people. So if I reduce that fraction, there is a 1 in 4 chance that the person who paid is sitting next to the window. Our last little thing to talk about is what is called a combination. So this works basically the same way as a permutation, only now the order that we place the things doesn't matter. So the number that we get should not be as high. So if you notice, what we're doing is we're still doing the factorial. We're still counting out the number of spaces that, based on the number of things we're choosing. Only now there was an extra factorial on the bottom to divide out the repeated combinations. So in terms of calculating this, your calculator has the NCR button the same spot as it does the NPR and the factorial. So really all you have to do is figure out which one you want so that when you type it in, you're telling your calculator to give you the right thing. So here's an example of how this will work. We notice that Monica has a chance to invite 6 of her 20 friends to join her at the park. She's going to choose them at random, and she wants the probability that these 6 specific people are chosen. So if we're being asked to go to the park, it doesn't matter whether you were asked first or last, or somewhere in between. As long as you got invited, you get to go to the park. So to figure out how many ways we can do that, since the order that the people are chosen does not matter, we're going to do 20C6 instead of 20P6 on our calculator. And if we do that, we get 38,760. So the probability that that one specific set of people gets chosen is 1 out of 38,760. All right, that's all we have for today. I will see you guys next time.